welcome to a new Voltlog. Today we're going to be talking about this cheap electronic dummy load that I got from banggood.com. It appears to be a very well built device, so let's get started. This thing came from banggood.com for $22 with free shipping. It was mentioned in a Voltlog episode number 37 together with more electronic items. So if you haven't watched that video, there will be a link on screen right now. The specs of the unit are maximum 9.99 amps and 30 watts, but limited automatically to 60 watts total power. We got temperature controlled fan speed. We got 2-wire or 4-wire measurements for battery discharge with automatic detection between the two modes. We got over temperature protection, reverse polarity protection, as well as other protections like over voltage and over power. The discharge voltage is between 1 and 20 volts in 0.1 volts increments. The discharge current starts from 0.2 amps and goes all the way up to 9.99 amps in 0.01 increments. The voltage measurement accuracy is 1% plus or minus 20 millivolts. The current measurement accuracy is 0.7% plus or minus 10 milliamps. And the capacity measurement accuracy varies according to the current that you're discharging. So for 0.5 amps we have 2.5%, for 2 amps we have 1.5%, and for 5 amps and above we have 1.2%. And the power requirements for this whole board to work, you need to apply 12 volts DC with minimum of 0.5 amps. Although Banggood doesn't offer much info, I did track this product back to who I believe it's the original seller on Taobao. It appears the seller also has a 110 watt version as well as an enclosure, which looks nice, and it would be a nice addition if Banggood would decide to carry it, because it's not that easy to get stuff from Taobao. I'm not sure, but I'm guessing the 110 watts just gets a bigger heatsink with updated firmware, so the new limit is at 110 watts instead of 60 watts. So just by looking at the unit, we immediately notice we have a heatsink plus cooling fan, so that's going to help dissipate the full rated 60 watts, because with just a passive heatsink of this size it would not be possible to dissipate more than 5 watts. It's made out of two boards, the main board and this riser display board. We have a rotary encoder, a tactile switch, as well as a bunch of LEDs and these 7-segment displays. I have taken these 4 screws out so that we can remove the display board and take a look at our main board. As you can see, it's connected through this 0.1 inch header, a really nice and friendly construction. First, we notice a small 2-terminal device stuck to the heatsink. I'm quite sure this one is a thermistor, and it's used to measure the temperature. Next we have our big MOSFET transistor and a dual Schottky diode in a TO220 package. Also here is our shunt resistor, and judging by the seal screen, it appears to be a 10 milliohm shunt resistor. We can see an op-amp right here. This one is more certainly in the control loop, and we also see a microcontroller. It's an STM-S series from ST Micro. This is an 8-bit microcontroller. On the left we have the DC input to power the load, and on the right we have the load input and the voltage measurement connector for the 4-wire mode. Also we can see lots of passives on this PCB, lots of resistors and capacitors in 0805 package. Overall a nice layout. And I say it's a nice layout because it looks nice, but also if you take a look at the bottom side of the PCB, we see very few tracks, so the designer did a good job routing most of the tracks on the top layer. As we can see, this is not the average dummy load with just an op-amp and MOSFET. It has quite a lot more parts built in and a lot of functionality added in software. So let's turn it on and see what it has to offer. The dummy load has two operating modes, which can be selected at power up. So while holding this tactile switch pressed, while you apply power to the unit, you go into the selection menu. And let me show you. I am keeping the tactile switch pressed and I apply power. I continue to keep it pressed until I get this on the display, fan 1. This means function 1. You can use the rotary encoder to switch between the two options, function 1 and function 2. And you can apply your selection by pressing the tactile switch. After selecting the operating mode, you have the option of disabling the buzzer, and you can switch between the two options on or off by this rotary encoder. And once again, you apply your selection by pressing the tactile switch. Function 1 is the classic dummy load operating mode, constant current. You have the option of setting a low voltage alarm, and the dummy load will continue to burn power until you stop it. It will start beeping if the voltage goes below the set alarm, but it will continue to work and it will just try to keep that current constant. In this mode, you won't get any reading for power or capacity. Function 2 is intended for battery discharging. Still, we have constant current mode. We still have the option of setting a low voltage alarm, but this time when the load voltage goes below the set point, the load will stop, which is really useful for battery discharging because you want to discharge them up to a certain point. You don't want to damage your batteries by over discharging them. It also makes this very annoying beep, but I mentioned you could disable that at startup settings. Let's try to adjust our cutoff voltage. Right now it is set for 3.0 volts, and I know it's kind of difficult to see that because I have very bright lights in here, and this 7-segment display doesn't have enough brightness to cover that. So if I click the rotary encoder switch, you can see the volts LED light up, and now I can adjust volts, and I can adjust in increments of 1 volt, or I can press the rotary encoder again and this LED turned on, and right now I can adjust in hundreds of millivolts. So right now I will have my voltage set to 3.5 volts, and if I click the rotary encoder again, it switched to the amps range. Now I can adjust in increments of 0.1 amps, or if I click the switch again, this LED turned on, and I can adjust in increments of tens of milliamps. Now if my settings are all right, I can start the dummy load, but first let me just apply a power supply to the power input. Now I have both the power supply and the dummy load in frame, so the output of the power supply goes to the input of the dummy load, and due to the lighting conditions in here, these 7-segment displays both on the power supply and on the dummy load are quite hard to see. Actually, the display on the power supply is dimmer than the one on the dummy load, but my settings are 3.5 volts low voltage alarm for the dummy load and 0.2 amps discharge current, and on the power supply I have the output set at 5.00 volts. So I want to demonstrate that after starting the dummy load, the fan will start running, the dummy load will start loading the power supply, and if I lower the voltage on the power supply under 3.5 volts, we will get an alarm on the dummy load. So let's do that. Right now I am in function 2, so the second operating mode of this dummy load, which means we get volts, we get amp hours and watt hours display. Also, we're using the 2-wire measurement mode. It means the measured voltage is tapped off right here on the power input pins. And we can see on the power supply we also get a figure of 0.22 amps output current. So the dummy load is discharging at approximately 0.2 amps. Let's try lowering the voltage of the power supply and see the response we get on the dummy load. So I'm now at 4 volts, and as soon as I go down to 3 volts we should get an alarm on the dummy load. 3 volts. So now, because we are in function 2 operating mode, I'm just gonna stop this. The dummy load just stops when the voltage goes below the preset, because that means you are basically discharging a battery, and when you are discharging a battery you don't want to over discharge it and go below its lower voltage settings. So in this mode, the important thing to remember is that the dummy load will automatically stop when the load voltage goes below the preset. But if we go into operating mode 1, the behavior is a bit different, as explained earlier. So I have the dummy load set for a 3.5 volts low voltage alarm and 0.2 amps discharge current. I'm going to start the dummy load, and as we can see it is pulling 0.2 amps from the power supply. But now if I lower the voltage, we can see we just get an alarm, and we get this LED blinking, the buzzer is sounding. We do see the measured voltage is at 3 volts according to, and this is the same as we see on the power supply, but the dummy load doesn't stop. So in operating mode 1, the dummy load doesn't care if your voltage goes below the preset. It will just give you an alarm and continue working. It will just try to maintain that constant current at its terminals. The device seems to store and remember which mode you are in even after power off. It will also store settings for voltage and current for each mode independently, as well as the state of the run button, which is more a bug than a feature in my opinion. Because if I have my load set for, let's say, the maximum 60 watts, and instead of ending its run cycle I just power it off while it was running, then sometime later I connect the load to a device and apply power, what will happen is the load will remember its last state as running, and it will be a full 60 watts load the next second, possibly causing trouble. So you need to be careful to always turn it off before powering off. And let me just demonstrate that. I'm going to start the load. Yeah, we're below the set point. So now the dummy load is running, and let's simulate me turning off power to the dummy load. As you can see, the dummy load turned off. We get nothing on the output of the power supply. But if I turn the dummy load back on by reapplying power to its DC input, we can see the dummy load goes directly into run mode, which was its last state. And this is just something that shouldn't happen. The dummy load, it's okay if it remembers the all its settings, but if it's running or not shouldn't be a setting that should be remembered. It should just start as off every time you're turning on. As you may have noticed, the device has this pin header on the side, and we can see that better if I detach the display board. As we can see, we have a 6-pin header onto which I've soldered this 5-pin male header, and I will explain soon why only a 5-pin header. So starting from this side, first pin is marked G, that is ground. Next pin is marked R, that is our receive pin for this serial port. Next pin is marked T, and you've probably guessed that is our transmit pin. Next pin is marked L. I don't know what this pin does. It appears to be low all the time and doesn't change. I also tried pulling it high, but nothing happened. Next pin is marked F, and on this one we get a constant 50 kHz square wave, 50% duty cycle, no matter what. We just get that signal continuously. It doesn't change. It doesn't matter in which state the dummy load is. We just get that 50 kHz square wave continuously. And the last pin is marked VC, and this is our DC input voltage of 12 volts, and that's why I didn't solder any headers to this pin, because I don't need 12 volts. I suspected from the first moment that this is some kind of serial port, and I was right. After probing with the scope, I discovered the baud rate to be 115K. Under operating mode 1 or function 1, as is displayed on the device 7-segment display, we get constant data pushed out of the serial port. Each burst is composed of 3 bytes, 2 of which represent the measured low voltage, and the third byte is a status code, and I've only seen 2 values, 0 or 1. 0 means there is an error, and it could be any of the errors like low voltage, over temperature, over voltage, over power, and 1 means no errors, just running. Under operating mode 2 or function 2, we get nothing out of the serial port. I have also tried sending various commands to it, but it didn't seem to respond, so it might be that the software doesn't have any features implemented for that serial port and it's just used to push the measured voltage for some sort of external data logging and plotting. That would be useful when discharging a battery, for example. I was curious if this thing would survive the full rated 60 watts. So I put it through a small stress test, having it dissipate 12 volts at 5 amps, standing just like this on my bench, free air, with an ambient temperature of 26 to 28 degrees C. I then measured the temperature of the heatsink using one of these contactless thermometers. I just have one of these cheapies off eBay. And it slowly went up until it stabilized somewhere around 85 up to 90 degrees C, with the fan on full blast. I was surprised it stayed under 90 degrees for its full rated power, but having done so, it means this dummy load is fully capable of sustaining the maximum allowed load without catching fire. Knowing from its specs that it has thermal cutout, I wanted to test that feature, so I kept pushing 12 volts at 5 amps while blocking the cooling fan inlet. So I used one of those anti-static bags and placed it right here on the inlet of this fan. It sucked it it made it flush with the surface of the fan because of the suction, and the temperature of the heatsink started to rise until it went up to approximately 105 degrees C. And here is a short video while I was measuring that temperature. Do consider that it was quite difficult to get the hotspot in focus on the thermometer, and the hotspot is obviously this power MOSFET. I was expecting the thermal cutout to kick in at 100 degrees C, but seeing it wasn't happening and I reached 105 degrees, I stopped the test before the thing could catch fire. There is another method of testing the thermal cutout, that is by heating just the thermistor with some hot air. So let's try that. So for this simple test, I have the dummy load running a light load at just 1 amp at 12 volts, but that shouldn't matter as I am applying heat externally. I have this cheap multimeter with a thermocouple which is connected right here next to the thermistor. So right now we're measuring the temperature of the heatsink on that point. So basically it's the same temperature or approximately the same temperature that this thermistor is going to measure, because they are very close together. And I'm going to grab my hot air station, and I'm going to apply heat externally and see when the thermal protection kicks in. So I think the thermal protection kicks in at around 80 to 85 degrees C. And now we have OTP on the 7-segment display, and the dummy load automatically shut itself down, but continued to run the fan at full speed until the temperature decreased. So that's a good thing. It will automatically cut out, but it will continue to run the fan to keep things cool. By comparison, I am running the load at full load, and we can see there is approximately a 20 degrees difference between the case of the power transistor and the temperature at our thermistor. So that is due to different placement and the distance between the transistor and the thermistor, but also a difference in thermal resistance, because the heatsink and all the mounting points do add up as thermal resistance, and the thermistor is actually measuring 20 degrees below the power transistor case temperature. So that's why earlier, when I ran the dummy load up to 100 degrees C measured on the power transistor, the thermal protection didn't kick in, because the thermistor was actually measuring 20 degrees below. So I should have went up to 110 degrees C, and for sure the thermal protection would have kicked in, because we measured it earlier, and we saw it does kick in at about 80 to 85 degrees C measured on the thermistor. My final thoughts on this dummy load are very positive. I'm quite pleased with this buy. It's definitely worth the $20 price tag. I think I would pay approximately $5 to $8 more for an enclosure if it were available. The main drawback is that it only goes down to 0.2 amps, and it only works in 10 milliamps increments on the current range. That kind of resolution is too low for testing smaller batteries with smaller discharge currents. But I can understand where that limitation comes from. The thing is, if you want to have a higher range limit like this thing does, 10 amps, you need to have a small value shunt resistor like the 10 milliohm resistor they used in here. And with such a low value resistor, low currents are going to generate a very small voltage drop down in the noise floor. So the ADC and op-amp combination used in this dummy load cannot measure it reliably. So you have to software limit the thing to a minimum of 0.2 amps, because on that figure you get good reliable measurement. Even so, it is certainly a good dummy load to have around the lab, and I recommend you get one. A link for the product page will be in the description below. As always, I appreciate and reply to any comments you leave below, so let me know what you think. See you next time.